Good morning, everyone. My name is Yu Liu. Um, I'm from the Cox University at Potsdam, New York. Cox University is a small research in New York, located in the upper state, New York, in the United States. So my presentation, the paper topic is a comprehensive performance evaluation with GPGPU applications under STT-RAM based hybrid cache architectures. So everyone knows GPGPUs, general purpose GPUs, now become more and more important for scientific computing. If you check the top 500 supercomputer list, you'll find in recent years, all the new build supercomputers has lots of GPUs, like Summit and Titan in the Operation National Lab in Tennessee. So GPU become more and more important. And you guys may know that soft errors, because by the particle strike on the semiconductor devices, we may get some errors in computing. That's called soft errors. The probability of soft errors for the regular CPUs are very, very low. For single CPUs, very, very low. But now we have large-scale computing systems like GPUs. They have the latest GPUs used on the Titan Summit supercomputer have over 10,000 cores. And there are millions of GPUs using these supercomputers. So occurrence probability of soft errors has been boosted significantly. Then we need to figure out some solutions to address this issue while we still can keep acceptable performance. The STT-RAM is a non-volatile memory, but key thing is that it's soft error resilient in nature because of its internal mechanism. Okay, so it's an ideal candidate for soft error resilient solutions to replace the regular SRAM. But there are always some benefits. While we have benefits, there are always some problems. It suffers a large overhead of latency and energy consumption on write operations. Read operations are fine, but write operations, there are some big problems. So the industry is very hesitating to adopt STT-RAM into memory systems because they worry about performance. If you get some error resilient memories, but why you get super low performance, that's not what we want. But however, we also notice that the industry has not do a comprehensive evaluation on STT-RAM in the GPGPU's memory hierarchy for GPU's applications. So we need this kind of evaluations to provide different options to the field. And also we have analyzed the 10 years of research publications. We find that STT-RAM based cache is an ideal candidate for power efficient and soft error resilient memory with a broad computing application in the future. There's not applied papers focus on this area. So this definitely a hard research topic. Again, this paper did a comprehensive performance evaluation of adopting the STT-RAM into memory hierarchy of GPGPU's architecture. So surprisingly, none of the previous work has done a fair and comprehensive performance evaluations for GPGPU's applications. I mean, different cache associativity and different adoption plans. Right. People here understand cache very well. You know that different cache associativity, the performance is very, very different. We have the direct map, we have two-way associated, four-way associated, eight-way associated, and even fully associated cache. Right. And we have different adoption plans. So in GPUs, each core has 4 very small L1 cache, and all the cores have a shared L2 cache. Right. We may just use STT-RAM to replace L1, a single L1 cache or entire L1 cache, or all the cache in the memory hierarchies. Right. The more STT-RAM we use, the better software reading performance we will have. The research accomplishment provides useful options for the software reading GPGPU architecture design. So, earlier work has the large-scale study of sub-era GPUs on Titan supercomputers. And another earlier work is integration of a synchronized batch scheduling and parent-based allocation, but they don't care about the cache performance. Another one work on the methodology and tools for evaluating errors relating to GPU application, but it also is not for the memory hierarchies of GPGPUs. Okay. So in this paper, both latency, timing latency, and energy consumption of several STT-RAM adoption plans and different cache associativities are evaluated and compared in this paper. And we use a cycle-accurate GPU simulator called GPGPU Sim to evaluate the performance. And we also use NVSIM to obtain the latency and energy consumption per read and write access for both SRAM and STT-RAM. We see another piece of work. They just use some data from their citations, and as data is always changed. They don't base on any tool, based on any experiment data, just based on some assumption. So here we use a very popular simulator for long volatile memory performance. And we see obtain the data per read and write access for both SRAM and STT-RAM in order for fair comparisons. So that's default. We based on the NVIDIA Fermi architectures. We have which has 4 separate L1 cache, each core CUDA core, and 1 unique L2 cache. Okay, so this is a configuration. You can see that the size and the sets, block size, and weight for all the L1 caches and L2 cache. Again, like the read and write latencies obtained from NVC, shown in the table 2 and 3 in the paper. And also, we have multiple benchmarks. And there are selected benchmarks from 2 benchmark shoots. First one is the SBESC 2009, and the second one is Zodinia. And the most popular benchmarks for GPGPUs related research. Okay. So, like I said, we evaluate both timing and energy consumption, because there's major concerns adopting the STT-RAM into GPGPU's memory hierarchies. To understand energy consumption, STT-RAM-based architecture, the strict distribution of energy consumption also discussed that how much energy spent on read, how much energy spent on write, because write is our major concern. Have a summary before enters give more detailed information. The range of ratio time performance between STT-RAM adoption and using SRAM is from 1.19 to 2.4 based on different cache associativity. Right. We'll be presenting the following slides. It's not a surprise that the performance STT-RAM is worse than SRAM. That's under our expectation. Like we said, we may satisfy some performance, but we get some error readings. Right. But like I said, if the performance will get worse like many times, we have to give up this plan. But now it seems that our sacrifice is worthy. And for energy consumption, actually sometimes STT-RAM behave better than SRAM, but of course some scenarios behave worse than SRAM because for some cache comparison, different associativity and size, some reading performance a little bit better. STT-RAM better than SRAM. If we have a large number of read access to the caches, we may get some better performance. Okay. So this is timing result analysis. So if we're just replacing L1 data cache with STT-RAM, that means we only make the data in L1 cache sub-error readings. Okay. We can see that the direct map cache has worse performance. Okay. That makes sense because direct map cache has more conflicting cache misses. We have more cache access, right? So we may have the worst performance. Right? One thing I want to mention about the benchmark CP is very special. The performance is very same between the STT-RAM and SRAM. That's because of its sparse data access, not too much data access to L1 data cache for this benchmark. The second one replace all L1 caches. Right? Again, direct map cache has worse performance. Right? And the performance even worse than only replacing L1 data cache because now we have more caches using STT-RAM. Definitely, we have more write access. That's replacing the L2 cache with STT-RAM. Right? Again, that direct mesh performed the worst. And we see that average performance descending reaches only 26%, which is best among all adoption plans due to limited number L2 cache write access. We can hierarchy cache architecture, right? We use L1 cache to mitigate the L2 cache misses. And that's replacing all caches. Of course, we replace all caches when the most write operation, so the performance is worst. But even in that situation, it's still, again, the direct map cache is the worst, as we just mentioned, the reason mentioned. It's energy consumption. That's same thing that replace L1 data cache. It's better than the timing performance, like I said, sometimes the reading performance, for some configuration, STT-RAM is a little bit better than the SRAM. Okay, the DRAM map cache performed worse due to similar reasons. And we can see that the red is energy spent on writing. We can see that the more energy we spend on writing, the worse performance STT-RAM will have. Right. The same thing will replace all the L1 caches. Again, very similar analysis as timing performance. Again, the same thing to L2 caches because we have less L2 cache access. So the average is very good, almost same performance between SRAM and STT-RAM. So that's replacing all caches. Right. Our conclusion is very similar as previous slides mentioned. So based on concluding that we did very comprehensive evaluation between the STT-RAM and SRAM by different cache associativity and different adoption plans. The work includes a proper combination of cache configuration and adoption plan, may only result in slight timing performance drop and even equivalent energy consumption performance. In a word, we believe STT-RAM is promising. Thank you.